Welcome back. Today we're going to talk about graphs of rational functions. This is going to be the first part of the video. A rational function, as we've talked about before, looks like this. We're going to have an f of x that's equal to the ratio of two functions. So it could be, g of x over h of x. And to be considered a rational function, our h of x, our bottom, can't be equal to 0. That's going to be an important point that we discuss when we start to talk about asymptotes. But for it to be a rational function, h of x can't just be straight up 0. All right, first example. Find the domain of f, something we've done before, and use limits to describe its behavior, something we've done before, but at the values of x not in its domain. So that's a little bit different wrinkle. Let's look here first. I'm going to write the domain in a couple of different ways. For this one, my domain, I'm looking at what could possibly go in. And as we've talked about before, sometimes it's easier to think about what couldn't go in or what would break it. So we know that the bottom can't be equal to 0, and so that would mean x can't be equal to 2. So our domain is going to be all reals. X can't be equal to 2. Well, how do we write that in interval notation? That'd be negative infinity to 2, and also 2 to infinity, but 2 is not included. All right, that's the first part. Done. Second part. Use limits to describe its behavior at values of x not in the domain. Okay, so what values aren't in the domain? In this case, we want to do limits at x equals 2. What is the graph doing at that value that's not in the domain? And I want to pull up a graph here for you. Let's look at this. Let's type in a function. F of x equals, and 1 divided by x minus 2. Check it out. All right, if I put this keyboard away, check it out. I can obviously see that 2 is not included in the domain, which is what I know. There's a discontinuity there, which I know. But what is it doing? Is it going there and then jumping? Is it going there and then going to infinity, which is what's happening? And so we want to describe the limits at that point. So here's what we have to do. We actually have to do 2, because if we look at this graph, it's got one limit here. The limit goes to infinity here. And on this side, the limit also goes to infinity. But how do we say that? We say it in a two-part. The limit as x approaches 2 from the negative side. Check it out. So as it approaches 2 from the negative side, what is it doing? Where is it going? This is the negative side. It's going. What's it doing as it approaches x from the negative side? Well, that would be f of x. So the limit as x approaches 2 from the negative side of f of x is negative infinity. So as it comes from this side, going to negative infinity. The other half, so that's one limit. My other limit is as x approaches 2 from the positive side. Check it out. As it approaches 2 from the positive side, where's it going? Well, the limit of f of x would be equal to infinity. Okay, so that's describing the behavior at the values of x not in its domain. 2 is not in its domain, but we discussed those limits there. All right, see if you can try this next one. Got a little bit of a wrinkle in the domain because of our denominator, but I think it's something you can handle. So pause it, come back and check out the answer. All right, we're back. If I look at this function here, I know that the bottom can't equal 0, and so x squared minus 1 equals 0. We're going to set it equal to 0 and figure it out. Well, if I factor this, I have x minus 1, x plus 1. So x can't be equal to 1 or negative 1. And so the domain of f is going to look like this. Domain is reals, x not equal to negative 1 or 1. I could write it in interval notation also. So it's negative infinity to negative 1. Also negative 1 to 1. And also 1 to infinity. Well, if I check out my graph, look at what I got here. I already have it pulled up. 2 limitations on the domain. Not surprising here. Negative 1 and 1. That's what I found out. But how many limits am I going to have? Well, I've got a limit as it approaches negative 1 from the negative side. I've got a limit as it approaches negative 1 from the positive side. I've got a limit as it approaches positive 1 from the negative side, and I've got a limit as it approaches positive 1 from the positive side. So I'm going to have 4 limits here. So here we go. The limit as x approaches, and I'm going to go systematically left to right. The limit as x approaches negative 1 from the negative side is going to be infinity. The limit as x approaches negative 1 from the positive side is going to be negative infinity. Those are my first two. Those are two limits as it approaches one of the values not in the domain. The other ones are going to look like this: as x approaches 1 from the negative, and the limit as x approaches 1 from the positive. So let's check it out. As it approaches 1 from the negative side, it's going to be negative infinity. And the limit as it approaches from the positive side is going to be infinity. All right, so that's how that works for values not in the domain. We're kind of obsessing about limits in this section. And so in our next one, we're going to describe how the graph of the given function can be obtained by transforming the graph of the reciprocal function f of x is 1 over x, identify the horizontal and vertical asymptotes, and use limits to describe the corresponding behavior. Sketch the graph of the function. Whew. All right, a couple different things here. We need to describe the transformation. We need to ID horizontal and vertical asymptotes, so that's 2. I'll put this 1, 2, and 3. Use limits to describe behavior. 4. Sketch the graph. Holy cow, we got a lot going on here. Let's start this way. Let's figure out how it compares to the original. All right, so I'm comparing to 1 over x. So what happens? Well, obviously, the numerator gets multiplied by 2, and then we add 3 to the denominator, but think about what that means in terms of what we've actually done. We're multiplying the whole function, so if f of x equals 1 over x, 2 times f of x would be 2 over x. Well, check it out. That's actually really close, right? I just need this plus 3. And so I know that one of my changes is multiplying by 2. That's a vertical stretch, right? Another change is that I've added 3 to x. So I actually add 3 to x, and that would give me 2 over x plus 3. Well, check out what that means. The second change, if I add x plus 3, remember when it's inside the function, it gets shifted the opposite way. So if this is plus 3, that means it goes move 3 left. Well, that was fairly straightforward as far as the transformation there. The next example, we're going to have to do another little process, but that one we could do by just comparison. So I now have described how it was transformed. Second part, identify the horizontal and vertical asymptotes. Kind of a blast from the past here. Okay, so vertical asymptotes. What does that mean? That's restrictions on the domain. So if I look at the bottom, I've got x plus 3 here. So if x plus 3 can't be equal to 0, then x can't be equal to negative 3. So that means there's a vertical asymptote at x equals negative 3. Remember, for vertical asymptotes, we're looking for restrictions on the domain, right? For my horizontal asymptotes, remember that's Bobo, Betsy, Bo2, but we're going to find another little wrinkle on this principle in this section. So if I look at Bobo, Betsy, Bo2, I'm going to compare the degree of the numerator to the denominator. Well, I have bigger on bottom, so that means y equals 0 is a is an asymptote there. Okay, so now I need to, did that. Identify the horizontal and vertical asymptotes. Now I need to use the limits to describe the corresponding behavior, meaning as it approaches the asymptotes. So as x moves toward infinity, behavior x approaches infinity or negative infinity, and also behavior at asymptotes. Okay, so let's check it out. I'm going to divide this into two parts. For my vertical asymptote, I'm looking at the graph, right? So I just so happen to have this here, 2 over x plus 3. Let me eliminate these other 2 here. So check it out. I got it right. There's an asymptote, vertical asymptote at x equals negative 3, and I want the limit as it approaches from the negative side, and also the limit as it approaches from the positive side. So here we go. The limit as x approaches negative 3 from the negative side of g of x equals, so check it out. As it approaches from the negative side, it's going to negative infinity. So the limit as x approaches negative 3 from the positive side of g of x, and this is all notation, very important to write that correctly. As it approaches from the positive side, it actually goes to positive infinity there. Okay, and so very important to check out your graph there and understand that when it's asking you to describe the corresponding behavior, we're looking at vertical and horizontal. Horizontal asymptotes. Check it out. There is a horizontal asymptote at x equals 0. If I zoom out, check it out. Look at how this graph gets infinitely closer to 0. And so I want to know the limit as x goes to negative infinity of g of x. Where is it going? Well, the definition of an asymptote is as the end behavior approaches infinity, what value is it going toward? Well, in this case, this one's going to be 0, and the limit as x goes to positive infinity of g of x is actually equal to 0 as well, because these are going to 0 as my ends go to infinity. Okay, so we're describing the behavior for the vertical asymptotes, what's it doing as it gets there, and also as my horizontal asymptote comes into play as x moves to infinity and negative infinity. All right, here's one for you to do on your own. And so you're going to be comparing it to the original. You're going to be finding the horizontal and vertical asymptotes. You're going to be describing the end behavior as it moves toward the end. Oh, I forgot to sketch, didn't I? Okay, so if I've got a vertical asymptote at x equals negative 3, right there, it's going to sort of go, put in a asymptote here, and we'll put in our graph sort of like that. There you go. That's g of x right there. That's our sketch. That's our fourth one. So we did all 4 things. All right, so try this one. For the very first part, if you can't figure out how it compares, go ahead and skip down to the next part where you find the asymptotes and describe the limits behavior, and I'll show you how to work on finding what it equals in terms of comparing it to the original. All right, so pause here, try it, and we'll come back and I'll fill you in on the rest. Okay, we are back. When we're going to compare this to the original, we actually divide. Okay, so we're actually going to divide to compare, and I'll show you why. Compare. And so I'm going to do some polynomial division. So I've got 3x minus 7 on the inside, and I've got x minus 2 here. Now I'm doing it the long way. And so when I compare x to 3x, I need to multiply it by 3. So 3 times x would be 3x. 3 times minus 2 would be minus 6. When I subtract, check this out. And this would be plus 6, so minus 1. So what do I have? Well, I can't do anything else, so what the heck did I just do? My answer is 3x minus 7 divided by x minus 2 equals 3 plus my remainder. Well, my remainder is negative 1 over x minus 2. Well, check this out. Look at what is actually here. This is h of x. This is my original function, just actually divided. And so if I look at this, I'm going to rewrite it so you can see. negative 1 over x minus 2 plus 3. How does this compare to 1 over x? Well, obviously, I have done a negative out front, so I've got negative f of, and on the bottom I've got a minus 2, so x minus 2, and then I'm adding 3 to the outside. See how that compares there? So I actually divide, and I just compare it to my original. What is being done to the numerator? Well, I'm multiplying by negative 1 on the outside. Multiply the whole function by negative 1. Add 3 to the outside, and I've got 2 in the middle. Well, what are the changes? Number 1, left, right, 2. And 2 would be flip over x. 3 would be up 3. Okay? It's important to note this must be done before vertical translation. Why? Order of operations. Okay, you have to multiply by a negative. You have to multiply first before going up 3. Okay, well that's not all. Because what I'm trying to do is I am trying to find the horizontal and vertical asymptotes. I'm trying to describe the behavior at those places. So here we go. Let's check it out. My vertical asymptotes. What is not going to work for my domain? Well, x can't be equal to 2, so this is domain. X can't be equal to 2, so there's a vertical asymptote at x equals 2. Horizontal asymptotes. Where are my horizontal asymptotes? That's my Bobo, Betsy, Botu. Well, my degrees are the same, so the bottom equals the top, so it's a constant of 3 over 1. My coefficients right there, and so y equals 3 is a horizontal asymptote. Well, what does that mean for my limits? Let's check a graph here. H of x equals 3x minus 7 divided by, oh, it's not going to like that. H of x, we'll just start over. H of x is equal to 3x minus 7 divided by, and I think it's x minus 2. Make sure my function's correct here. 3x minus 7 over x minus 2. Okay, check it out. Well, what did we expect to happen here? We were expecting to have a vertical asymptote at x equals 2 and a horizontal asymptote at y equals 3. Let me zoom into my home here. Yes, there is a vertical asymptote at 2. Yes, it seems that there is a horizontal asymptote at 3. So let's describe our limits. Vertical asymptote, the limit as x approaches 2 from the negative side, and the limit as x approaches 2 from the positive side of h of x is equal to. So as it approaches 2 from the negative side, that car's driving, where's it going? Infinity. And the limit as it approaches from the positive side, that car is driving into negative infinity. The limit as x approaches infinity. Remember, horizontal asymptotes, we're talking about infinity. And the limit as x approaches negative infinity, h of x. So, where's it going? Zoom out. As it approaches infinity and negative infinity, where's it going? And because it's a horizontal asymptote, and the definition of an asymptote is what value does does the h of x approach as it goes to infinity and negative infinity? Those are both going to be 3. Okay? So, any questions about that? Please fill them in the margin or send me an email, or we'll talk about them in class. Thanks for watching, guys, and we'll see you next time.